incompatibility. Thank you.
Thank you so much for the introduction. And so also thanks a lot for organizing this amazing event again, and very happy to come back again and to present some of our recent findings. And also, by the way, I just recovered from sickness, so I lose part of my voice. So it sounds a bit weird, but okay. So today I will briefly talk about some of the recent works that I collaborate with my friends Gu Huanyu, Constantino Budroni, Chen Xiliang, and Chen Yunan. And we want to ask the question, which is, can we stochastically distill quantum theory and measurement incompatibility? So as the first part of today's presentation, I'll briefly introduce or say recall the formulations of these two quantum resources. And then later on, we'll also talk about what do we mean by saying that we want to stochastically distill them. And then the last part of the presentation is I will come back to the question that I posed here, and I will try to answer this question. So let's now start with measurement compatibility, especially what it means and how to formulate and define it. And in order to understand this quantum resource, it's important to have this notion, which we call measurement assemblage. So this is used to characterize a set of quantum measurements. So you can imagine that it is a box with different buttons that when you click on different buttons, it will implement different quantum measurements. And more precisely, mathematically, it can be written as a collection of positive operator value measures. So in this collection with a given and fixed x, it will be a positive operator value measure. So it is a collection of different quantum measurements. And when we have this notion, it turns out that it's fundamentally important to know whether such a notion is genuinely different from a single measurement or not. Or in other words, do we really need to use this notion to describe everything on Earth, or actually everything can actually be described by a single quantum measurement plus some classical data processing? So in order to answer this question, we need to analyze the case when there's no multiple measurement inside the box. And what can we do in such a case is that rather than having multiple measurement inside the box, we only have a single measurement, which is the G lambda that you see here. And rather than implementing different measurements when we click on different buttons, this box will do something like always let the input state go through the same quantum measurement, and then there will be some classical post-processing based on the button that we click on. And overall, if we don't know the detail of the box, we will still get some measurement outcome. But then if it is something from a box like this, then the measurement outcome must be described by the summation that you see here. And this is what we call joint measurability. Because if the measurement outcome can be described by this, then it means that we can just use a single quantum measurement plus some classical post-processing to simulate the output. So now, a fundamentally important question is, can measurements always be jointly measured? Because if this was the case, then we don't really need to use the notions of measurement assemblage. We can just focus on a single measurement because everything could just be described by a single measurement and some classical probability distribution. And luckily, the answer to this question is no, because there are some measurements that cannot be jointly measured. For example, if you consider the poly x, y, z, then these collections of measurement just can never be described by such a box. And this is what we call measurement incompatibility, because they cannot be jointly measurable. So now we know the notion of the first quantum resource that we want to consider in this project. And now let's move to the next one, which is called quantum theory. In order to formulate quantum theory, we need to use the so-called steering scenario, which is a bipartite setup containing two agents, say A and B. And suppose that they share a quantum state rho AB, and we further assume that in system A, they have a measurement assemblage, which is the notion that I just introduced. And steering scenario is a multi-round setup such that during each round, a referee will somewhat announce index X randomly, and the referee will further inform the agent A about the index X. Then the agent A will just apply the corresponding measurement in the given measurement assemblage, and then send the classical outcome to the agent B. And if you combine everything together in the system B, we will have this subnormalized state. which we collectively call it state assemblage. And importantly, in such the so-called steering scenario, there is a no signaling condition, which is, if you look at this scenario, the only way for the agent A to signal B is through this dash arrow. So if we just basically sum over all possible outcome A, meaning that we just get rid of this dash arrow, then there should be no further way to signal B from A. So this is the so-called no signaling condition in the steering scenario, which means that if we sum over A, then in the system B, we always have the same state, which is also called the reduced state of a state assemblage. So this is a steering scenario, and just like the case in measurement assemblage, we can ask the same question: is that what is the role of the bipartite state rho AB and quantum measurement here in describing everything that we can observe here? So in order to answer this question, we need to analyze the case, but there's no bipartite state in quantum measurement. And similar to the Bell scenario is that in such a case, what A and B can do, or more precisely, what A can do is that they can have some random variable, or say the so-called local freedom variable, using it to prepare some local state in the system B, and then further use some conditional probability distribution to further process the classical data, or say classical index announced by the referee. And in such a way, there's no need to have any bipartite quantum state and quantum measurement in the system A. And you can still prepare some state assemblage in the system B. But in this case, if a state assemblage is prepared this way, it must be expressed in this form, which is the so-called local hidden state model. And similar to the case of measurement incompatibility, now it is important to ask, can state assemblage always be described by local hidden state model? And again, luckily, the answer is no, because there are some state assemblages, they just cannot be described by local hidden state model. In such a case, we say that the local agent A can steer the local agent B quantum mechanically, or in other words, we say they demonstrate quantum steering from A to B. So this is just like a very brief introduction of quantum steering, which is the second quantum resource that we want to consider today. And it seems like that, so at the first glance, it seems like these two things are somehow irrelevant to each other, but it turns out that they are strongly related in the following sense. Let's go back to the steering scenario. Sorry. Let's go back to the steering scenario, and then it turns out that what we can prove, or say, is a well-known fact, is that if the state assemblage that you see here, which is the sigma, if it is steerable, then the underlying measurement assemblage must be incompatible, and the bipartite state behind rho AB must be entangled. So this somehow shows that steering implies measurement incompatibility. And the converse direction is also true in the following sense, that if we have a measurement assemblage that is incompatible, then there always exists at least one bipartite state, such that you combine them together, they will demonstrate quantum steering. And actually, this bipartite state can always be chosen to be maximally entangled. So in this sense, for a very long time, people believe that quantum steering and measurement compatibility, they're operational equivalent. They are just different phases of the same physics. So for a very long time, people believe that if we can do something for quantum steering, then we should also be able to do so for measurement compatibility. Just like if we could do stochastic distillation for quantum steering, then maybe we should also be able to do so for measurement compatibility. But is it really the case? So as I will tell you the answer later, it remains to know what do I mean by saying that now I want to stochastically distill quantum steering and or measurement compatibility. So the idea of distillation is that, at least the very first motivation I believe is that we start with some not very good resource, and we want to use certain weight to extract the higher value of the resource. For example, we start with a weakly steerable state assemblage sigma, and we want to know that whether there's a way to distill steering from it. So a very natural way to think about this is that suppose that this is weakly steerable, so the resource of the value of this resource is very weak, and we can consider multi-copy of this and then apply some like global operation such that in the end we can extract probably one copy of a highly steerable state assemblage. And this is what we call multi-copy distillation. And it has the advantage that has been known for a very long time, has been studied for a very long time, but experimentally it's really expensive. And as one of the objectives of this project is that we want to focus on the protocol or say the scenario of distillation that will be at least feasible and then actually budget friendly for our experimental collaborators. So this motivates us to think about a different way out. So from here you can see that for multi-copy distillation, we are using the space as the cost. We increase the system size. So we also need to have the ability to control like a large system. A different way out, or say alternative way to do this is that we again start with a weakly steerable state assemblage, but rather than using the space as the cost, we now use the time as the cost. So we let the state assemblage undergo a filter, which is a quantum operation with certain probability to fail. That when it fails, but when it succeeds, we get some better quality of quantum steering. And this is what we call stochastic distillation, which is really doable in experimental setup relevant to our projects, such as nitrogen vacancy center or quantum optics. So that's why in this project, we focus on this type of distillation, because we really want to know basically how far we can go when we only use stochastic distillation. And we also want to know what will be the limitation of such a distillation. So we are eventually at the position to talk about the main result. And let's talk about the first part, is that can we stochastically distill quantum steering? And the answer is yes. In fact, it has been shown experimentally, so the answer must be yes. But we can actually go beyond answering this question in a binary sense, because we can prove the following equality, which can even tell us the physics behind the stochastic steering distillation. So due to the time limit, I cannot tell you the detail behind the equality and how we prove this, but we still have time to briefly illustrate the physics behind. So the first thing is that the IR and SR here are two well-known and commonly used figure of measures to measure incompatibility and steering. So the SR is the so-called generalized steering robustness, and the IR is the so-called generalized incompatibility robustness. And of course, we consider other types of figure of measure in our paper, but then again, due to the time limit here in the presentation, I only focus on the relation between these two. So let's look at the right-hand side of this equality. So the right-hand side means that we start with a state assemblage sigma, and then we want to know what is the highest achievable steering on the local filter, which means that the physics of right-hand side is the highest distillable steering on the, or say in the stochastic distillation scenario. And if we now look at the left-hand side, it is the incompatibility of something that we call a B sigma. It has a name which is called steering equivalent observable, but well, basically you can just view it as something induced by sigma. It's a measurement assemblage induced by sigma more precisely. So the left-hand side is incompatibility induced by sigma. And this equality thus told us two important physical messages. The first one is that steering can be stochastically distilled. It is because we can find examples such that the sigma, which is the input of our state assemblage, it can have a very weak steering, but as long as the incompatibility, which is the left-hand side of the equality, is high enough, then we automatically prove that you can do stochastic distillation for steering. And the second thing is that we also uncover the fundamental limitation of stochastic steering distillation, which is set by incompatibility. Because this equality tells us that incompatibility induced by sigma set the highest or set the optimality of the stochastic steering distillation. So this equality not only answers the question, or say the first half of the question in the positive, but also telling us the physics behind, and also give incompatibility a new physical meaning. So now let's move to the second part of the question. Can we stochastically distill measurement compatibility? So at first we thought that the project, once we answer the part for steering, should somehow be complete, because for a very long time we believe that steering and compatibility are basically the same. Until this project that we found that it turns out that we cannot stochastically distill measurement compatibility. So in order to understand what we mean, the first thing is to know how to filter quantum measurements operationally. Again, because we want to have a scenario that our experimental collaborators can really demonstrate for us in lab. So we want everything to be like doable and then very intuitive for them. So how to filter quantum measurement? And when we talk about filtering state assemblies, it's actually quite straightforward, because if you have a quantum state, you just let it undergo some quantum operation with certain probability to fail. So that's very intuitive to define. But how to filter quantum measurement? So mathematically, if we want to filter quantum measurement, it means that it is a map acting on the POVN element. But what we can do in lab is that we can prepare state, we can do measurement. So what we see here will be what we can do in lab, or what we can do operationally. And everything here, it turns out I would say the map E dagger is actually in the so-called Heisenberg picture. So if we map it back to the so-called Schrödinger picture, we get something like this. And because of this is the most natural thing that we can do in lab. So in this project, we view this as filtering measurement. So when we say filtering quantum measurements, we actually means that we filter their input first, because this is what we can do in the lab. So with these notions of measurement filters, now we can prove why it is impossible to filter and then enhance measurement compatibility. Let's start with two lemmas that we can prove. The first one is that if we have a given measurement assemblage, then its incompatibility robustness can be expressed by this maximization. And this maximization is taken over all possible state assemblage tau that can be prepared in this steering scenario. And especially, it is a maximization over all possible local filter in the system B. And this is the first lemma, but then we actually can also further show that it's sufficient to consider special types of filter of this form. And you can still express incompatibility robustness as a maximization, which means that the maximization is only needs to be taken over all possible local filter of this form. So by using these maximization as an operational definition, or say operational form of incompatibility robustness, we can now see whether we can use measurement filter to enhance, or say to increase the value of this one. But once we put the filter inside this operational scenario, then we can again move from the Heisenberg picture to the Schrödinger picture, and then using the property of phi plus to move from the left-hand side to the right-hand side. And then the final step is to notice that these two things will together give you, again, another filter. And now using lemma 1, we know that the incompatibility robustness is actually a maximization over a possible filter, which means that this one can just never be more optimal than the optimal one. So combining everything together, we show that no local filter can really help us to enhance measurement compatibility when it is measured by IR, which is the incompatibility robustness. And we also show the same result for other figure of merits of incompatibility robustness. So this somehow suggests that it turns out that it is impossible to distill measurement compatibility stochastically. So to summarize, we asked the question that, can we really stochastically distill quantum theory and measurement compatibility? And we show that it is possible for quantum theory, but it is impossible for measuring compatibility in relevant figure of merits. And we further show that measurement compatibility sets a fundamental limitation of quantum theory stochastic distillation. And finally, this talk is based on these 3 papers, and thank you very much for your attention and patience.